All right, so let's see. Announcements. You may have noticed there is a midterm. Midterm grades are all graded. They're up. They're on Panda Grader. Solutions are also up. Please take a look at those and make sure everything's okay. If you have any regrade requests, there's a post on Piazza about the details about how you do that. But the fuse is short because we want to get all of those regrades regraded. So you only have about a week. The midterm was a little hard. We know this. And so we injected some points to put things back on track. And I just wanted to let you know we really do care about these things, and we do not make the midterms purposely hard to make you suffer or anything like that. We try to make them kind of challenging but fair, and if things don't kind of work out, then we'll adjust them. Any questions on anything midterm related? All right. Let's continue talking about Bayes nets, which you've been talking about for the past couple lectures with Peter. So today we are going to talk about an idea called independence, which isn't really about Bayes nets busting loose the way it looks like in this drawing. It's about being able to tell in a network what things influence each other and what things don't. So as you may have noticed, we're diving into the deep end as far as probability goes. And today's going to be no exception. So I wanted to make sure we're on the same page just in terms of the checklist of rules. The laws of probability are few, but the ways in which we kind of remix them are many. So it's a lot like when we were learning Bellman equations, and there are kind of only a couple things going on, but they happen in every possible combination. It's the same thing here too. So let's just make sure we're not in symbol shock, because you're going to see a lot of probabilities and conditional probabilities and p's and x's and y's and vertical bars. Let's make sure we know what these things are. So the key thing, by now you all know what a random variable is and what a distribution of a variable is. The key thing that we're working with in this unit is this idea of conditional probability. And everything else we do in Bayes nets is really about building one kind of conditional probability out of another kind. So conditional probability looks something like this. It's the probability of some outcome x given some conditioning information y. Now, why would we care about a conditional probability in an AI class? Well, in general, we have uncertainty about our world, and we have observations. And the evidence we have about the world is the y. And the thing we're trying to predict is the x. So really, any time you're trying to reason about something you don't know on the basis of something you do, with uncertainty in the mix, it's going to be conditional probabilities. That's why this is at the heart of this middle part of the class. So x given y, that is what's shown here is the definition. So there's no assumptions here. It's actually very important with Bayes nets. We make assumptions everywhere. It's important to know what comes from an assumption and what just comes from the laws of the math. So this is a definition. This is the definition of conditional probability. X given y is, the probability of that is the probability of x and y occurring divided by the probability of y. And the way you think about that is, with respect to the chances of y, what's the chance of also x? Okay, that's the definition of conditional probability. You should also know the product rule. In fact, you shouldn't just have it memorized. I should be able to wake you up at 2 a.m. and you should just start saying the product rule before you're fully woken, right? So the product rule says this, all right? The product rule, let me just write it out. The product rule says p of x and y, the probability of x and y happening in words, that's the probability of y happening and, which means multiplication, the probability of x happening given that y happened. Okay, and you may look at that and be like, okay, I don't like that product rule, I want the other product rule. Okay, that's fine too. It can also be the probability of x happening and then y happening given x. Okay, so these are called the product rule, but they're really just the definition of conditional probability where you multiply both sides by p of y. So again, it looks like we have 2, maybe 3 rules here. We've got 1. It's just the definition of conditional probability with terms moved around algebraically. Okay, so in neater writing than mine. And then the important one that's going to be most relevant for what we're doing today is the chain rule, which is just kind of the product rule all grown up. So if we have, for example, 3 variables, we could say the probability of x and y and z all happening for certain values. Well, we could say that's the probability that x takes on that value marginally. Then, given that we know x, it's the probability that y takes on that particular value times the probability that z takes on its value given x and y. Okay, so a couple things to point out about the chain rule. One, this isn't the only chain rule. You don't like this chain rule, go get your own. You can do P of z times P of y given z times P of x given yz, right? You can order the variables in any way. The important thing about the chain rule is you introduce one, then the next, and each one conditions on everything that went before. Now, again, the chain rule sounds like yet another thing to remember, but it's really not, right? It's really just math. So P of x, that's just P of x. What's P of y given x? By the definition of conditional probability, that's P of y given P of y and x divided by P of x. And what's P of z given xy? Well, that's P of z and x and y divided by P of x and y, right? That's just definitions of conditional probability, and then we go on a canceling spree, and we're done. So the chain rule is really still just this definition of conditional probability worked out. Okay, so conditional probabilities, product rules, chain rules, if you got all that, you're most of the way towards Bayes nets. It's important when you see this, though, we're often going to write this in this generic way, where we have n variables, and we just write a product over P of xi given the variables that have come before. So this is a lot of symbols. This just says each variable conditioned on the ones that come before it in the ordering. So how many orderings are there? There's n factorial. You can have any ordering you want. All right, still the chain rule. Questions on these? All right, we have one more important concept, which is in general important, but it's going to be particularly important today, is this concept of independence, right? And so we talk about random variables being independent. Intuitively, that means that the value of one and the value of the other, well, they're independent, right? There isn't a correlation between them in some particular mathematical sense, but we have to nail that down. And the way we nail that down is we write, well, it's a condition, right? You saw this last lecture, some joint distributions over x and y have the property that x and y are independent, and some don't. So if I hand you a conditional distribution, complete with all the gory numbers in it, I give you the whole table, and I say, is this thing, does this joint distribution over x and y I just gave you, does it have the property that x and y are independent? You would say, I don't know, let me go check. And so what you do is you would check every value of x and y, you'd look at their joint probability as given by the table, then you would look at their marginal probabilities, right, which you could also compute from the table. We'll talk a little bit more about that in the next lecture. And then you'd multiply them together. And if it turned out that the joint probability was equal to the product, well, that means the chances of x and y happening are the same as x happening and then y happening, regardless of what you knew about x. Okay? And there's actually something very important about independence. So if I changed it minorly, right, and if I said, no, the condition is that P of xy has to equal P of x times P of y, but I stuck in a given x, right? Now it's not some special property. Now this is true of every distribution on the planet, because that's just the definition, that's just the product rule, right? That's just what conditional probabilities are. So the key thing here really is that it's true it's not just the product rule, it's also true with x dropped, right? All right, so if your distribution, which may or may not have this magical property of independence, if it has the property that for all x and y, the joint distribution is equal to the product of the marginals, then we give it a stamp and we say it's independent. Similarly, we have a more complex notion of independence called conditional independence, where we say x and y are not independent necessarily, right? They're independent conditioned on a third variable. And so here what we have to check is we have to look at all values of x, y, and z, because it's a statement about three variables, and we have to check to see whether it's the case that the probability of x and y, let me lift this up here. We have to check to see if it's the case that the probability of x and y given z now decomposes into x given z and y given z. My pen's not cooperating, but there you go. Okay, so if this is true, then we say that x and y are independent conditioned on z. I'll make that appear in nice LaTeX, okay? So we write that this way. So if they're marginally independent or they're independent given no evidence, we just write x, weird perpendicular thing, y. And if they're conditionally independent only given some evidence, we write x independent of y given z. This thing here is red independent, and it's supposed to look kind of like an orthogonal symbol, right? Meaning they're at right angles. So if you have some geometric intuition, some linear algebra here, then maybe that's going to evoke independence. But it's just a symbol. Okay. Any questions on the slide? This should all be like burned into your retinas by now. All right. All right. So those are all the laws of probabilities. Nothing in there involved Bayes nets, right? That was just probability distributions over multiple variables that sometimes have certain simplifying properties called independence, where some variables don't have all of the complex interactions that mathematically they might. Okay, so what's a Bayes net? You've already seen some examples, but formally a Bayes net is just a giant joint distribution over many variables, one variable per node. And the reason why we don't just write out a giant table with all the probabilities is a Bayes net is a much more compact encoding, and there are lots of nice ways to reason with them. So I give you a Bayes net. It's got some variables and some arrows, and we're going to see what lives inside a Bayes net in a second in a demo. But once I give you this Bayes net, it's a description of a domain. It's a model. So you can either think about it mathematically as a joint distribution over a bunch of variables, or you can think about it kind of functionally as a model. I ask questions of this thing. So it's kind of like a database. And if you think about it, a joint distribution is a database. It's a big table of numbers, and you can ask various things about it. So one question you ask is, what is the probability of something given some other thing? What is the probability that the ghost is right in front of me given that I'm hearing a clanking sound to my left? Okay, which is more or less what your project 4 is going to be about. Okay, but there are other questions like what Bayes net is appropriate, what distributions can a Bayes net encode. These are more mathematical questions on the surface, but they're also modeling questions. Help us figure out which Bayes net to use. And then finally, there are the direct modeling questions, which if I describe a domain for you and you know, let's say you know how a car works and you want to create a Bayes net to diagnose car start failure or something like that, then what variables do you connect up? What does it mean to draw an arrow? So let's maybe start with a demo so we can make all this very concrete. So, all right, here's our empty Bayes net. Let's build a Bayes net together. Let's see, do we want to build an interesting Bayes net or the alarm? Oh, this hurts a little bit to do this, but let's get the alarm network up here. Okay, have you guys seen the alarm network? Yes? No? Raise your hand if you know the alarm network. All right, good. So let's build the alarm network in the applet. So in the alarm network, let's see, there's this kind of key central variable, which is alarm, right? So we can call this thing not node 0, but alarm, right? And so let's see what we've got. It's got a name, that's the random variable. It's got a domain, just like a CSP node. These are the values of the random variable. In this case, it's a Boolean variable, so its domain is true or false. But we could call it kind of, if I had a not symbol, I could call it A and not A or something. I think the applet will scream if I put an exclamation point. But we can call them anything we want. We can call them true and false. All right, so now we suddenly have this alarm. And in this Bayes net, it's already a Bayes net. It's over one variable. And if I look under alarm, what do I see? I see a probability distribution that I get to specify. Like I can say the probability of the fire, or sorry, this is an earthquake alarm. The probability of the alarm going off is 0.01, and the probability that it's not going off is 0.99. So great, here's your first Bayes net. What question can you ask? All you can ask it is how likely is the alarm, and the only thing it's going to tell you is 0.01, right? So not particularly interesting. Bayes nets are interesting when you add other nodes and you add effects. So for example, one reason why you might have your house alarm going off is that there's a burglary. So this is the example from the book. All right, so here's burglary, here's alarm, right? But we want more than that. We want a connection between them, right? Because we're going to do the math today to figure out why it is that burglary and alarm are independent, but just visually it doesn't make any sense that they not be connected. If this were a CSP, you would want a constraint between them. And the analog in a Bayes net is you want an arc between them. So let's create an arc. All right, so now we've got a two-node network that says there are variables burglary and alarm. And now if we look under the hood, we're going to see that under burglary, we get to specify how likely the burglary is, 0.5. That's bad. You don't want to live there. Let's live somewhere where the burglary is 1 in 1,000 or something like that. Let's actually check what's on the slide. Okay, burglary, 1 in 1,000. Great. Okay. All right, now what's living under alarm? This is the interesting part, right? So before, when we just draw a node, it basically says how likely is this node to be on, right? How likely is this alarm? But now this node has a parent. And in a Bayes net, what that means is we're specifying how likely the alarm is, not in a vacuum, but how likely it is for each condition. So we look at the parent, we say, okay, alarm depends here on burglary. So if I look underneath, I get a table that tells me the response. Think about this as saying how alarm responds to the value of burglary. So if burglary is true, well, maybe the alarm, maybe it's a pretty good alarm. So maybe it goes off 90% of the time, 99% of the time. And if there's no burglary, then it's, maybe the false positive rate is 0.001. Okay, so I have to specify the conditional distribution over alarm, which is, you can think of this as, if you think about it logically, you want to say something like, if there's a burglary, then there's an alarm, right? And if there's not a burglary, then there's not an alarm. But instead of saying logical things, we write down exactly what the probabilities are so that we can balance things that might not work in a logical setting. All right, what else is in the alarm network, or what else is in the burglary network? Right, there's a node for earthquake. Okay, and what does earthquake have to do with the alarm? What's the idea here? If you're up on your alarm networks. What's the story? Yeah. Yeah, the earthquake could set off the alarm. So we say, okay, I know what to do. The earthquake causes the alarm, right? So I draw an arc between earthquake and alarm. Okay, but now something interesting has happened. Alarm has two parents, and remember that what variables do in a Bayes net is they tell you how likely that node is for all of the different settings of the parents, right? So we want to write rules intuitively, like if burglary, then alarm, if earthquake, then alarm, but what if there's a burglary and an earthquake, right? And so the way that's all resolved is we zoom in on alarm and we look under the hood, and now you can see there's an even bigger table living there, because I need to specify how likely it is for the alarm to turn on with burglary and earthquake, no burglary, no burglary. I hope I got them all in there. You get the idea. So I would have to go in here and specify all these numbers. Okay. Point. Okay, it's definitely going to go off if they both happen, but if there's an earthquake, maybe 80% chance, and that's fine. Okay. So I don't know if those numbers made any sense. If I were actually an alarm engineer or a whatever, I would have to think a little bit longer. All right, and then there's these other two variables, which is, I guess this is my friend Mary, and she might call me or not, right? And so I create an arc, and now what I'm doing is I'm saying, how does Mary behave? She's part of my model now, and I have to say how she behaves. And maybe she like calls me or not, and it depends only on the alarm. So if there's no alarm, then maybe she never calls me because she hates me. But if there's an alarm, maybe half the time she'll just figure if she doesn't call me, maybe she'll get robbed too. So there's Mary. And then we can add somebody else. So I forget who the other person is. Mary, non-Mary calls. Okay, so we're going to stick non-Mary over here. And non-Mary is a much nicer neighbor, and she's just kind of always calling to talk. So I can fill in her probability table. I'm doing this as a domain expert. There's no right or wrong answer as far as the applet, but they encode different distributions. So alarm, I don't know, if the alarm goes off, she's definitely going to call me, but if not, she might call me half the time anyway just to talk. All right, so now I've specified all these numbers I specified, right? They talked about the specific interactions, how burglary affects the alarm jointly with earthquake, right? How Mary responds to the alarm or not. And now I can ask questions of this thing, right? So I can say, all right, how likely is it that Mary's going to call me? Or actually, let's look at non-Mary. That's better. Okay, remember she calls me half the time just anyway, but 0.9 of the time when there's an alarm. So if I look in, let's just do brief. If I look in, I say, okay, she's going to call me 66% of the time. Okay, I think actually I left the probability of earthquake at like 0.5. You don't want to live there either. But the thing is, she calls me like half the time when there's no alarm, and mostly all the time when it does. So the overall probability is 0.66, which isn't a number I entered, right? It comes from crunching the numbers I did enter to form these other quantities. So that's the story with Bayes nets, right? You design the network, and it encodes a joint distribution. You don't specify all the elements, you specify little pieces. But once you've specified the pieces, you've essentially nailed down the whole joint distribution in a way we'll make precise, and then you can ask questions of it. Okay, here's the kind of things that we want to talk about today. Well, let's make a query. How likely is burglary? All right, answer, 0.001. That makes sense. I entered that number in when I created the Bayes net. Right, but now, let's say I discover that Mary, who hates me and does not ever call me, has called. Now what happens when I query burglary? Should it be higher or lower? Higher, right, if this thing is kind of working. All right, so yeah, it's gone from like 1% to 2 or 3%, right? And that's just because of how these specific numbers fall, so it's twice as likely there's a burglary if I get a call from Mary. Okay, I could manipulate the numbers and you get different outcomes, but for this Bayes net, that's the answer. Okay, fine. Now here's something interesting. It was 248%. Let's say I observe let's say I observe, well, let me get rid of Mary here. All right, so now if I do my query, just so the numbers are nice and neat, I look at burglary, and now it's 0.001. All right, let's say I observe that there is an earthquake, right? Maybe I get a call from the geological survey, right? And now I know there's an earthquake. What happens to the burglary probability? I don't know, let's find out. Okay, answer, nothing, right? So in this particular network, nothing happens. So interestingly, it seems like the probability distribution over burglary doesn't change when I observe the earthquake. So in this case, I would want to be able to talk about something like, maybe this appears that burglary and earthquake are independent in this network. So even though there's arrows that kind of connect them in some indirect way, they seem to be, at least from this one test, which isn't exhaustive, right? But from this one test, they appear to be independent. And so maybe I didn't even have to do all the work this applet is doing. I can look at this and I can say, just from the structure of the network, I know these two things are going to be independent. So we're going to spend a big chunk of today trying to answer that question. Is this node and this node independent given some evidence? And the idea is going to be, if the answer is yes, then you know you kind of either don't have to do a query or you can speed up the algorithms we're going to see in the next few lectures. Okay. Any questions about the applet? Yep. Can I put a loop in? Only if I want the laws of probability to come crashing down around me. So the rules here is it has to be a directed acyclic graph. And there's a deep reason for that. It has to correspond to an ordering of the chain rule, where each variable conditions on variables that precede it in the chain rule. So it has to be acyclic. There has to be some linearization of it. And if you put in, if there are cycles, then you'll break probability, and we don't want that. Yep. Okay, so will it? I don't know. Well, this is a question about the applet, right? So I don't know. Let's find out. No, it just won't let you do it. So this applet is very protective of math. Okay, so yeah, I think in general, just don't mess with math. The answer is, the BaseNet is not just, it's a graph, right? And so as a graph, like as a data structure, you can add an arc in the other direction. But the semantics no longer kind of make sense. It no longer defines a conditional probability in a well-formed way. Right. Okay, so good time to talk about BaseNet semantics, right? So what is a BaseNet? It's a direct acyclic graph, one node per random variable. Each variable represents something that's going on in your domain that you may or may not observe and you may or may not query. Underneath each node, just like we saw in the applet, is living a conditional probability table. And that conditional probability table is essentially like a little if-then statement. It says how that variable will respond to the settings of its parents. So for each setting of the parents, it says whether that variable is going to be on or off, but it says it in a probabilistic way. A BaseNet encodes a joint distribution. How does it do that? Well, if you have a bunch of variables xi, then what we do, this is kind of maybe the most important formula from today, we define the joint distribution over our variables x1 through xn as follows, right? Here's a recipe for computing a number in this probability table, right? You go through the variables one by one and take their product, right? So you go through the variables one by one, and for each one, you multiply in the probability of the setting you're interested in, given the setting of the parents, right? And that makes sense, because that's what's in the network, all right? Now, is this going to give a well-formed probability distribution? Who knows, right? Well, I'm going to have to prove some things about it, but this is a procedure for constructing a number. Okay, so we're going to see some examples of that. Okay, I sometimes call this the BaseNet reconstitution formula, right? You have a BaseNet in pieces, and this tells you the full joint distribution by putting those pieces together, right? Just add water. Okay, so here's the alarm network, right? The graph is the same thing you saw. I guess it was John was the other neighbor. Okay, this is the graph that you saw in the applet, and all of these probability tables, they live inside, right? So this marginal distribution over E, it lives there, and this one lives there. I should make them thought bubbles, right? And this big one here, this is the probability of A given the alarm, given burglary and earthquake. This is the big table, and it lives underneath, it lives inside A, right? So graph structure, a graph topology, and conditional probability distributions at each node that tell you how that node responds to its parents. All right, now how do I ask a question, what is an entry in this table? Well, what I would do is I would say, what's the probability of some setting? Okay, what is the setting? This is the probability that there's a burglary, no earthquake, the alarm goes off, John doesn't call, but Mary does, right? Why would I care about this specific setting? Okay, because to answer other questions, like what's the probability that Mary calls me given a burglary, I need to compute a bunch of these things and add them together. Next lecture, we'll talk about inference. But for now, just think about the goal is to answer single questions from this database by essentially joining stuff together. All right, so how would I do this? Well, the Bayes-Net reconstitution formula says you go to each variable, plugging in the relevant values. So I go to B, and I would plug in P of plus B, because that's what it says, which is in fact 0.001. And then I go to E, and I plug in P of minus E, because that's the relevant value, and that's 0.002. And then I go to A, and I plug in plus A, and what do I condition on? Well, I condition on whatever the Bayes-Net tells me to. In this case, it's B and E, so plus B minus E, and I plug in a number, so that's plus A plus B minus C, that's this number, 0.94, right? And I go along, and I look up all of these numbers, and I multiply them together, right? Each one is a line in the formula, and I multiply them all together, and I get some number, okay? Should be obvious that I get a number that's kind of between 0 and 1 because I just multiplied a bunch of probabilities together. It may be less obvious that this is in fact the joint distribution and what assumptions I've made. Okay. All right, that's how you look up a number. Any questions on that? Okay. So sizes. Why would you do this? When you build this Bayes-Net and you put down all of your variables and you draw a couple arcs and you enter some probabilities, how many numbers do you enter? Well, it depends on how many parents things have. Remember the applet? When it was just the alarm, I entered like one number. There are two numbers, but they determine each other. Probability of alarm. But once it had two parents, I needed to say an alarm probability for all 4 combinations of the parent. Okay, so how big is a Bayes-Net? How big is the joint distribution over all the variables? Let's compare these things. All right. On one hand, we have a full joint distribution over n Boolean variables. What's this look like? It's a giant truth table, right? It says for each value of variable 1, for each value of variable 2, for each value of variable 3, and then there's a number that's a probability, and all these many numbers add up to 1. So if these are Boolean variables, how many numbers are there in these in this truth table, right? This giant joint probability. Well, there's n axes. Each one has a true and a false, so it's going to be 2 to the n, right? So 2 to the n. That's big. That gets big very quickly. A reasonable sized Bayes-Net might have something like 1,000 nodes in it. That's just totally off the table. Okay. So 2 to the n. Joint distribution, very big. You're not going to ever write down 2 to the 100,000 variable values and so on. How big is a Bayes-Net over the same variables? Well, it's going to depend. It's going to depend on how many arrows are in that network, right? Well, each node has a certain size. So let's imagine each node is basically the same size as each other node. This can't actually be true, but it's fine. So we imagine that there are now n nodes, each of which has k parents. Now, how big is this thing? Well, it's n times however much space it takes to store a single node. And what's a single node? It's like some probability of x whatever given kind of k other variables. Well, so how many conditions are there? Well, there's the 2 to the k ways you can assign the parents, and then for each one there's 2 numbers. So the answer is this one is going to be, each node is going to be 2 to the k plus 1. It's exponential in the number of parents, but it's only linear in the number of variables, the number of these things you have, because each node is kind of separate from the rest in terms of its data storage. Okay, so this is much better. If k is small, it doesn't really matter if n is big. And this is really the beauty of a Bayes-Net, is you can describe a very complicated domain with very complicated interactions as long as each node doesn't have too many parents. So although the interactions may be complex, they're kind of locally simple. And often the real world is like this. X causes Y, Y causes Z. And so even though there's maybe a ripple effect, the direct connections are few. So, yeah, you can think of this essentially, you've got kind of these little conditional probabilities, and you combine them together, and they represent a big joint distribution. So if you put them all together, foomp, you got this giant joint distribution. In the next lecture, we're going to figure out how to make sure we never do that, right? So implicitly, they're going to represent the joint distribution, and then implicitly, we're going to compute some quantity, but we're never going to reconstitute the whole behemoth. Okay. So the Bayes-Net itself and the joint distribution it represents both let you calculate entries in the joint distribution, which we'll see means it lets you calculate anything you want, right? Because everything else is just sums and divisions of those things. But the Bayes-Net has a huge space saving. Also, I can ask an expert question. I can go to a doctor and I can say, how likely is it that somebody with the flu is going to have nausea? Right? I can either ask the doctor for a qualitative sense, or I can go check medical records. That's easy. But it's very hard to say, how likely is it that somebody who is age 28 and has a mole on their left arm, and you if you condition on everything, how likely is it that they're nauseous? I don't know. I've never seen someone just like that before. So you want to break these things up into simple pieces if you want to be able to get the numbers from people, or the data, really. All right, Bayes nets are also going to be faster for answering queries. It's going to be just like a Bayes net. If the just like a CSP. If the structure is simple, you're going to be able to answer questions efficiently. Any questions, all that? Okay, so check mark, representation. We now know what a Bayes net is, what it represents. It represents a joint distribution. We also know the all-important reconstitution formula that says if you want an entry of the joint distribution, you multiply together all of the local pieces as appropriate. Now what we're going to do is we're going to talk about conditional independence. Okay, next class we're going to talk about inference, which is how you compute things like the probability of x given y. Today we're just going to think about what kinds of answers you're going to get and how the structure of the Bayes net is going to determine what kinds of distributions you can represent. Okay, the other stuff will come later. Okay, so conditional independence. So we say, and this is something you should at this point should be recap. We say x and y are independent if it's the case that for all x and y, the joint probability equals the product of the marginal probabilities. Okay? And we write x independent of y. We say x and y are conditionally independent given z if that statement is true, but only when you condition on z. And we'll see examples. In general, conditional independence is a little bit more common. Right. So for example, here's this little domain, which hopefully is familiar. Right. Here you have fire. There may or may not be a fire. That's one random variable. Then smoke. There may or may not be smoke in the air. And then the last variable is the alarm. The alarm may or may not go off. Right. So 3 variables. And we wouldn't say, for example, the alarm and the fire are independent. Right. That would mean the chance of the alarm going off, it has nothing to do with whether or not the fire goes off. In particular, the chance of the alarm going off is the same whether or not the fire is on. If that were true, what would you do? You would take the smoke alarm back, right? Right? The whole purpose of the fire alarm is to go off when there's a fire. So it's clearly not the case that the alarm and the fire are marginally independent, right? But it is true that that at least in a simplified model of this, you might find that the alarm is independent of the fire given the value of smoke. What would that mean? It would mean if there is smoke, then whether or not the alarm goes off is independent of whether or not the fire is there. Why? It doesn't matter whether the smoke came from the fire. It doesn't matter what came from your handheld smoke dispenser. It doesn't really matter. The point is the alarm is only looking for the smoke particles. It doesn't really matter how they got there. So once the smoke particles are in the air, it doesn't matter where they came from. Similarly, if there's no smoke, even if there's a fire, right? I don't know, if you're somehow vacuuming up the smoke, the alarm's not going to go off. It doesn't know about the smoke, right? So provided this is the way your fire alarm works, this conditional independence might plausibly be true. Okay. Now you're going to be tempted to say something that you're going to be tempted to say every time I show you a simplified domain. You're going to say, okay, right, but a good fire alarm is going to look not only at smoke, but temperature or whatever. Okay, fine, right? This may be false in a more complicated domain. And in general, this is always going to be true with modeling. There's going to be a primary effect, like, primarily the smoke is what turns the fire alarm off. But like, if there's a fire, maybe it's going to melt the fire alarm and then it won't turn on anymore, right? So there's always going to be these secondary things where a really detailed model, yes, there is a direct dependence, but it's weak. And there's always a trade-off between adding the important ones, but once you add too many, the Bayes net gets complicated and you start having inferential problems, both in terms of the speed and also the statistics in estimating these things. Okay. All right. So, important warning. Bayes nets have inside them conditional independence assumptions. So in particular, we had the Bayes net reconstitution formula, and here it is. This is essentially the key part of it. So let me actually just go off slide here for a second. We know that the Bayes net reconstitution formula says if you have x1, x2, x3, that is probability of x1 given whatever parents it has in the Bayes net times probability of x2 given whatever parents it has in the Bayes net times probability of x3 given whatever parents it has. And that's going to vary network by network. But at the same time, we have another way of building joint distributions called the chain rule, which says this is equal to the probability of x1 times the probability of x2 given x1 times the probability of x3 given x1, x2, right? So, Okay, so how do we reconcile these? Well, it turns out if you kind of do pattern matching, you can say, well, if probability of x1 of xi given all the previous variables just happen to be the probability of xi given its parents in the Bayes net, right? If that were true, maybe it is, right? If that were true, then these two ways of building a joint distribution are the same, right? The chain rule is always true, and so essentially if this equality is always true, then the Bayes net reconstitution formula does the same thing as the chain rule. And so what does that say? What does it mean for these statements to be true? That's a conditional independence assertion, right? It says that P of x1 given all its parents is the same as P of x1 P of x1 given everything before it is the same as P of xi given just its parents. Okay, so those independence assumptions are essentially required by the chain rule. But there are going to be more. There's going to be a bunch of other independence that comes from other ways you could order things and looking at other collections of variables. And you get these off the graph. Okay, so what we're going to do now is we're going to go look at various Bayes nets and we're not going to ask what the probabilities are. We're not going to ask what is P of x or whatever. We're just going to say from the structure, what kinds of independences can I read off? Okay, so let's work through this example in a few minutes. Let's take a break now, and then we'll work through the cases on conditional independence. Okay. All right. Any questions before I get started again? Okay, so here's a Bayes net, right? Before we've been telling stories, this one doesn't have a story. It's just there's some variables. But even without knowing what x represents in the real world, and without knowing what exactly P of y given x is in the little conditional probability table, I can still answer some questions about this network without actually knowing the numbers, the parameters. In particular, I can look at this and I can say, well, I know that P of x, y, z, w, I know that this equals P of x times P of y given x times P of z given xy times P of w given x, y, z. Right. Why do I know this? Is this true of this network or of any joint distribution? Any joint distribution. That's the chain rule. That's always true, right? Just in your head, see all those conditionals as ratios and canceling everything out. It's true. Okay. But I know something else, right? I have a recipe for computing entries x, y, z, w, right, from the reconstitution formula. It says, go variable by variable doing variable conditioned on parents. Well, that's P of x, it has no parents. That's P of y given x, because x is its parent. So far, they look the same. Okay, except now I get here, and the reconstitution formula says, if you want this entry of the joint, you multiply in P of z given y. Okay, whereas the chain rule said, given y and x. All right, similarly down here, this says multiply in P of w given what? Z. Z and anything else? No, just z. All right, so I've got this, which is true kind of mathematically for any distribution. I've got this, which is the definition of this joint distribution. And so I can actually, I can conclude some things. So in particular, I can just kind of pattern match and read off from this that it must be that for all x, y, and z, it must hold that P of z given y equals P of z given x and y. Okay, and if that's true for all values of x, y, and z, what does it mean? It means once I know y, the value of z doesn't actually depend on x. So this is in fact equivalent to z being independent of x given y. Okay, so this conditional independence holds not in any joint distribution, but in the one that's defined by this network. And it's true because of how we multiplied these things together and which things had which parents. And I can read it straight off the chain rule. Okay, similarly, I can go over here and I can get a kind of a statement that says, well, it must be that P of w given z is P of w given x, y, z. Okay, and that's going to say that conditioned on z, w is independent of kind of x and y together, right? And then it turns out if you do a little bit more math, that means it's independent of x and it's also independent of y, but we don't actually have the machinery right now to do that, and it's not kind of blindingly obvious, but it's reasonable. Okay, so the point is, there's certain conditional independence assumptions, this is the most obvious one, that can be read directly off of the simplification in the chain rule, right? But those specific independence assumptions aren't the only ones. There are other ones that are implied. For example, if you look at this, it kind of seems, you could ask, for example, is x independent of w? Well, the chain rule doesn't tell you, but it looks like the answer is probably no, right? Because x seems to cause y seems to cause z, and z seems to cause w in some intuitive level. We'll make that precise later. But it looks like probably x here is independent. So what do we know? We know x is independent of z given y. That comes from the chain rule. But it looks like probably y is independent of w given z, right? It's kind of the same thing down a little bit in the network, right? And this one you can't instantly get off the chain rule, though like I said, it's almost there. So what we want is we want a way of looking at a network and figuring out whether independence assumptions, which look like this, which are backed by equations like this, which hold for all values of the variables, whether or not they're true purely based on the structure. So we've already found some. We've looked at the structure of this, and we found that x and z are independent given y. What about the rest? Okay, so this is an important question about a Bayes net, right? I show you a network, and for now, I'm not going to show you the parameters, the specific probability of alarm. You don't get to see that. You only get to see the variables and how they're connected, right? So this is a lot like in CSPs, where we said these two components are these two components are disconnected, meaning I can solve them separately. Right? And in fact, a lot of those same ideas about independent subgraphs or tree structure are going to turn out to be just as relevant here in CSPs. Okay, in Bayes nets. Okay, so I give you a Bayes net, and one question is, are two nodes independent given some particular evidence? Okay, if the answer is yes, we can actually prove it with algebra, though you wouldn't want to. If the answer is no, we can prove it with a counterexample, because remember, an independence assumption is a system of equations that all have to hold that say this times this equals that. Right? So if it's false, I can dig up a particular example that shows that those equations don't hold. So proofs of independence are by algebra. Proofs of lack of independence are by counterexample. Okay. So here's an example. X to y to z. It's a simpler version of what we saw in the previous graph. And we might ask the question, are x and z necessarily independent? Right? So we know from the previous slide that they should be independent given y, but intuitively they shouldn't always be independent, right? And so how do we show that the answer is no, they're not necessarily independent? And well, we can do it by example. We can say, all right, let's imagine that x is the low pressure system from last time, and y is rain, and z is traffic. Right, well then intuitively low pressure causes the rain causes traffic, and no, the low pressure and traffic aren't independent. Okay, now that's not really an example. That's an intuitive reason why the example should work. If I wanted to actually show you this, well then I haul out the numbers and I actually multiply everything together and I work it all out and I show that here's a setting of this for which this probability isn't the same as that other probability. Okay, but I'm not going to go through that now. That's super tedious. I will do some of the proofs in the other direction. Okay, so we'll come back later. So now we're going to talk about a general algorithm for answering this question. Are these two variables guaranteed to be independent given some evidence based on the structure of the graph? And the algorithm we're going to have is an algorithm called deseparation, right? And you can think about this, okay, here's this Bayes net, it's a bunch of these circles connected together, and the basic idea is sometimes when you observe evidence, it breaks the graph into kind of two pieces. This should remind you of something like cut-set conditioning. When you set the value of a variable, suddenly now pieces that used to be coupled are no longer coupled. Okay, and that's the basic idea of this algorithm. We're gonna set evidence variables and we're gonna look for paths, right? But it's gonna be a little more complex than it was for CSPs. Okay, so here's the outline of how we're gonna figure out the deseparation algorithm. We're gonna look at triples, small little 3-node graphs, because they're small enough we can actually work out the algebra without it being too messy. Then we're going to show how you can take a complex graph and break any question into a question about a bunch of different triples. So we're going to reduce any big question to a question about these kind of base cases that we're going to understand well. And deseparation is going to be an algorithm for doing that. Okay, so we're going to see all of the triples. There aren't that many triples. If you have three nodes that are all connected in a path, right? We're basically looking for paths, right? There's really not that many ways you can do it. So we're going to look at all of them and we're going to memorize them. There's like 3, okay? So this configuration here, where you have x pointing to y, pointing to z, okay? So these little eyeball-looking things are the variables. So this example is x is low pressure, y is rain, z is traffic. And we call this, this configuration a causal chain, right? Because the idea in the domain, though that has no role in the math here, the idea in the domain is that x causes y and y causes z, right? In the math, it is simply these 3 variables with the arrows going left to right in both cases. So what does the reconstitution formula say? It says this. Okay, it says the joint probability of x, y, and z is p of x. Okay, that's because x has no parents. Y given x, because x is a parent of y. And then z given y, because in this network, z has y as a parent, but not x as a parent. Okay, and this is almost the chain rule, right? Almost the chain rule. The chain rule would require x to be living there as well, but it's not. So, is it guaranteed that x and y are, that x and z are independent? Okay, and the answer is no. We saw that before. If I actually want to prove that they might be dependent, I have to show you actual numbers. Okay, and so here's one. This is super simple. They're not even probabilities, right? They're just, they're all deterministic. So if I want to write down low pressure causes rain, rain causes traffic, and so on, I might in numbers write this down. The probability of plus y, which is rain, given plus x, which is low pressure, is 1. Okay, that's an extreme case. It's deterministic, but it works here. Probability of minus y given minus x is also 1. So essentially, x and y always have the same value. And y and z similarly always have the same value. Now, if I plug and chug on these, I can show that, that the probability of z is 0.5 if x is equally likely to be either. But the probability of z given x, it's completely determined. Okay, so this is a particular case of numbers that demonstrate empirically, right? Sorry, they demonstrate by counterexample that x is not necessarily independent of z, which we already got intuitively. Okay, the more interesting part is this. What happens if we ask the question, is x independent of z given y? Okay, this says, is the chance of traffic, does it depend on low pressure if you already know that it's raining, right? And you might think the answer is, yeah, they should be independent because it doesn't matter where the rain comes from. It could be coming from airplanes overhead dropping the rain. It's the rain itself that causes the traffic, not the low air pressure, right? Now again, this is modeling. You could be like, oh, but when the air pressure is low, the driver's teeth hurt and they don't pay attention. Like secondary, right? Secondary effects. In the primary model here, the way we've drawn it, there's no direct influence, right? Okay, so how can we show this? Well, we start with we start with a conditional probability. So we want to know if x is independent of z given y. So we write probability of z given x and y. Okay, well, that is equal to p of x and y and z divided by p of x and y. Why is this true? Definition of conditional probability. Always true. We haven't used this network at all. However, this network allows us to simplify. This network allows us to say that the probability of x and y and z is p of x times p of y given x times p of z given just y. And in the denominator, I can write p of x and y is p of x times p of y given x. Okay, what licenses the one in the denominator? Product rule. Always true. It's just a chain rule. Chain rule of 2 variables. Okay, now I can go on a canceling spree, and I see that p of z given x and y is equal to p of z given y if you build your joint distribution according to this recipe. Right, that's essentially our assumption. All right, well, if p of z given y is the same with or without x, that means they're conditionally independent. Okay, so the equality of these 2 things in purple boxes, that is the statement x is independent of y given, x is independent of z given y. Okay, so that would all have appeared and is in your notes. Okay, So yes, x and z are independent once y is observed. Okay, so somehow y breaks the connection. It's kind of like a cut set. Okay, and informally we say evidence along a chain blocks the chain. Okay, here's another configuration. Okay, this is called a common cause configuration. So this is where you have a variable y, and then variables x and z, which both directly depend on it. And you can see that in the math, because the probability of x, y, and z is p of y. It has no parents. And then x depends directly on y, and z depends directly on y. Okay, but z doesn't depend directly on x. So an intuitive illustration of this would be y is the variable whether or not there's a project due, right? And then sometimes the forums are busy, that's x, and sometimes the lab is full, that's z. And so it might be that if you kind of observe the world, you'd be like, the forums and the lab, they get busy together, right? Sometimes they're both busy, sometimes they're not both busy. But it turns out that they're both tend to be busy when the project is due. Okay, and it might be that the forum is busy because people are complaining about the lab being full, but probably not. The primary effect here in this model might be that the project being due causes people to go to the lab, and it also causes people to go to the forums. Okay, and that's what's reflected in this equation here. All right, so there's a common cause. So is x independent of z marginally? Well, seems like it shouldn't. And in fact, I could give you specific numbers because it seems like in this domain, it seems like if the math kind of works out intuitively, then when the forums are busy, the labs also tends to be busy. So they kind of co-vary in this way. All right, so I can give you a specific set of conditional probability tables, which is that the project directly causes both. And to make the example simple, we do it with deterministic cases. So essentially, if the project is due, then the forums are busy and the lab is full. But if the project isn't due, then neither the forums are busy nor the lab is full. Okay, and then if you plug and chug on these numbers, then you'll see that the independence property doesn't hold. Yes, question? Yeah, so there's another Bayes net here, which adds that arrow. This Bayes net would be appropriate if you had a kind of substantial dependence of x on y and z together. Okay, it's a more complicated model, and it's not the one we were talking about. But it's still a Bayes net. It's just not this one. Right? It's like a CSP. You can add more constraints. It's just a different CSP now. Okay, so in this configuration, which is a cause with two effects, right? If I don't observe anything, if I have no evidence, then the effects are correlated, right? Because if one effect is true, then the cause is probably true, and that means that the other effect is probably true. So in this case, x and z are not marginally independent. However, what happens if I observe the common cause? So now I know that y is true. Okay. Well, if I know that y is true, maybe x and z no longer have a direct interaction. So we can again prove this in this Bayes net, not in general, right? Because there could be other arrows. In this Bayes net, we just start with the definition of conditional probability, and then we simplify. So we say, well, in this Bayes net, this is p of y times p of x given y times p of z given y. And then in the denominator, that's p of y times p of x given y because of the product rule. And then I start canceling things. And now I have the statement that z given x and y is the same as z given y, and that means conditioned on y, z, and x are independent. Okay, so now I've done a small bit of algebra, and I've shown that in a network like this, if I have evidence here, then the two effects are now conditionally independent. Okay, there's one last structure. So that was two structures, right? There's the chain of reasoning, x implies y implies z, and the common cause. You have y, and it kind of independently creates x and z. There's one more triple that's important. And the last configuration is what's called common effect. And this is the one where all of the kind of pain and suffering comes from. Okay, the last configuration has to do with two different causes of the same effect. And so that's triples like this, where you have x here, y here, z here, and x and y kind of both cause z. This is like the alarm. It had two causes, the earthquake and the burglary, and because of that it was complicated, because when you have two children, that doesn't make the Bayes net more complicated. Each child kind of looks at you independently. But when you have two parents, suddenly you're entering all these other numbers because you have to describe the joint interaction between those parents and this node. And that's why this situation is kind of a pain. So here's an intuitive example from the rain example last time. If X is whether or not it's raining, Y is whether or not there's a ball game, and Z is whether or not there's traffic, you might say, well, rain causes traffic, and ball game causes traffic. And yeah, if there's rain and ball game, you're going to get even more traffic. Okay, but the rain doesn't cause the ball game. Okay, and again, you could be like, oh, but they might cancel the ball game if there's rain. Secondary, right? In this network, we've chosen not to model that arrow, and so we get what's called a V structure. It's called a V structure because it looks like a V. Okay, for once we have a name that makes sense. All right, so are X and Y independent, right? Is whether or not the rain happens and whether or not the ball game independent? Well, it wouldn't be if there's an arrow between them because rain cancels the ball game. But assuming the ball game happens rain or shine, like no, some days there's a ball game and some days it rains and they don't interact. Okay, so these things are independent, right? If they don't interact, then they're going to be independent, and even though they both cause the traffic, they're not marginally correlated here. So you still have to prove it, and you prove it by writing down probabilities of X and Y, and you cancel some things, and I'm not going to do it. You can try it. Okay, but this is actually interesting, because before, when we had chains, right, X, Y, Z, right, X and Z were kind of they were coupled until you observed Y, and then they became independent. And when you had common effects here, Y, X, Z, right? X and Z were coupled until you observed Y, and then they became independent, right? And the evidence broke things into two pieces. Here it's different, because here we just saw that without evidence, they're already separate, even though there's no evidence between them. X and Y here are already separate. Okay, so the rules are different in this case. And then here's the weird one. Thought that was weird. Okay, are X and Y independent given Y? Well, we just said the rain happens or it doesn't, and there's just days when there's a ball game, and those are just independent random variables. But what happens when you observe traffic? Suddenly something weird happens. When I observe traffic, what's my thought process? My thought process is, well, either it's raining or there's a ball game. Okay, but if these two things are both rare, there probably aren't both. Which means in some sense, when you observe the traffic, you know one of these things is happening, but probably not both, and that means that now they're in some kind of competition. It's called causal competition in this particular case. And so once you observe the traffic, intuitively it seems like X and Y, which were previously independent, are suddenly coupled, because they're competing to explain the evidence. Yep? Thank you. Now the slide is correct. Good catch. Other questions? Okay, but the key idea here is right, which is that in these V structures, everything is backwards. That the two causes are independent until you see that the common effect happened, and now suddenly you're in a race to see which causes is actually happening. Okay, and it's backwards. So here, when you observe evidence, it somehow activates the influence between X and Y here, between the rain and the ball game. They have nothing to do with each other until you see the traffic, and you now know it must be one. Okay, think about it this way. I buy 2 lottery tickets, right? And their winning chances are independent, right? They're just 2 independent lottery tickets. But then you observe that I'm really excited, and I have a shiny new $100 bill. Well, probably one of the lottery tickets won, but probably not both, right? It's so rare that they win. And so suddenly you've got these 2 tickets that were independent, but now your belief should be that one, but probably not both of them are winners. And now they're coupled. Okay? Okay. So, what's the general case? We saw all these little cases, and I was illustrating them with intuitive configuration so you can remember them, but in the end, the answers to yes, they are guaranteed to be independent, no, they're not guaranteed, come from counterexamples with real numbers and algebraic manipulations, okay? Not from appeal to the laws of traffic. if there are laws of traffic. Okay, the general case. So if you want to compute conditional independence, you chain together these three cases over and over again. Okay, so the general question is, here's a Bayes net, like this guy, and I pick two variables, and I say, is this variable and this variable, are they independent? Or I say, are they independent given some evidence? And the solution to this question is you're going to analyze the graph. You're going to look for paths in the graph, basically, right? And the paths are going to break down into triples. And if all of the triples kind of match up to these examples that we've already seen, that will give you your answer. So let's see how it works. First, we're going to do it wrong. So first, we're going to do it the way kind of our experience with CSPs would suggest. So here's a recipe for this algorithm. We take our network. In this case, hopefully this it looks familiar. L is low pressure. Low pressure causes rain. Rain causes traffic, but ball game also causes traffic. Rain also causes my roof to drip. Okay, this is the Bayes net. Now you could look at this and be like, I don't like this Bayes net. I think rain causes ball games to be canceled. I think low pressure causes traffic because of driver toothaches. I think that when my roof drips, then it spills out into the road in front, right? You can add arcs all you want. This is the network we're going to go with. So the questions we're going to answer are for this version of the network. Okay, so the recipe is we're going to shade the evidence, and we're going to look for paths. So here's one attempt. Let's say you want to answer, is the low pressure independent of the traffic? Okay, intuitively, what's the answer? Do low pressure and traffic, are they independent? So if there's traffic, does that change your belief in low pressure? Okay, you're going to symbol shock or something. This is just the real world. Remember, low pressure, okay, maybe you just don't have strong opinions about air pressure. Okay, if you see traffic, does that change your belief about whether or not my roof is dripping? Yes, because your reasoning should be, well, there's traffic, that means there's a pretty good chance of rain, and when there's rain, my roof drips. So seeing the traffic changes my belief of roof dripping. That means that we'd like the answer to be that T and D are not guaranteed to be independent, right? If they're independent, that wouldn't happen. So far it works pretty well, right? I find a path between them, right? And if along that path I don't hit any evidence, then it looks like it might work. Let's do it again. Let's say you see there's traffic and you know that it's not raining. Okay, if you know that it's not raining, does seeing the traffic change your belief about my floor? No. Right. So far this almost works. It says in your giant graph, whatever it is, try to get from the one variable to the other, and if you hit any evidence, then the path is blocked, right? And that path somehow represents the flow of information or something like that. This algorithm is almost right. Try to find a path, but stop when you hit evidence. Okay, this is almost right. Where does it fail? Okay, where does it fail? It fails like this. I might ask you something like, okay, I don't know anything about traffic or drippy floors. Is rain and ball game independent? We know in this model, yes, they are independent, but there's no evidence between them. But the path between them doesn't have evidence, but it does go through a V structure, which was the weird case. Okay, so maybe you try to find a path and you stop when you either hit evidence or a V structure. Okay, and more or less now you're starting to build the right algorithm. So here's what you actually do, right? It breaks at V structures, and somehow the V structure is backward. For most triples, you can get through them unless there's evidence. For the V structure, you can only get through it if there's evidence. So here are the triples, right? Okay, in all their gory detail. So here is a causal chain with no evidence in the middle. Evidence, kind of information can kind of flow right through. Here's common cause with no evidence. Okay, if you have a triple that's either a causal chain or a common cause, basically the rule is like the simple algorithm. You can take your path through the middle node unless it's observed. If it's observed, then it's blocked. Okay, so for these configurations, they're called active if the middle variable is unobserved, and they're called inactive if the middle variable is observed, right? And inactive triples block. They block evidence. Okay. However, for V structures, it's backwards, right? A V structure is only going to be active, meaning the variables on either side are now correlated. It's only going to be active if the bottom of the V structure is observed. Otherwise, it's inactive. There's one extra case which is important and slightly weird, which is that a V structure is activated not only if the base of the V is observed, but if there is any evidence that descends from it. Okay, that is, if you go back to here, R and B, rain and ball game, are independent until you observe traffic, and now suddenly they can become dependent. But if instead of observing traffic, you observed a traffic report, that would also be enough to make them dependent, right? So V structures, they're backwards from the other cases, and what activates a V structure is either an observation at the root of the V or some descendant of that. So this is the special case that's going to trip you up. Okay, so here's the algorithm. I ask you a question. I say, are X and Y conditionally independent given some set of evidence variables? And the answer is basically going to be a search problem. Okay, well, what you're going to do is you're going to look to see whether there are any paths that connect X and Y up. And if all the paths are blocked, then X and Y are separated, and that means they're independent. Okay, and we say they're deseparated in that case by Z. Okay, so the rule is you look for all undirected paths, and for each path, you check whether it's active. What does it take to make a path active? A path is active if every triple in the path is active. And a triple is active if it's either a causal chain or a common cause where the middle is unobserved, or it's a common effect of V structure where B or one of its descendants is observed. All it takes to block a path is a single inactive segment. But in order to break X and Y apart and make them conditionally independent, all potential paths need to be inactive. This is actually something that's maybe a little clearer once you've worked some examples. But that said, does anybody have a question I can answer at this point? Okay. So, deseparation algorithm, you get a query. Here's the query and a whole bunch of new notation. It says, is this variable independent of this variable? So, I said that in the wrong order. Is xi independent of xj, given some set of evidence? Well, the recipe is you check all of the paths. The arrows are relevant to whether or not the path is active, but it's not relevant to the set of paths you have to check. So you check all undirected paths between xi and xj. And if at least one path is active, then independence is not guaranteed. But if all paths are inactive, then independence is guaranteed. Let's do some examples. Okay, here's an example. Are R and B independent with no evidence? So you can think back, if you want to kind of intuit the right answer, you can think back to the domain. But if you want to do the algorithm, then it shouldn't matter. So in this case, I'm asking whether rain and ball game are independent. Answer should be yes. Let's check our algorithm. What paths exist in this graph? Well, there's only one. It's this R to T to B path, right? Okay. They'll be independent if this path is inactive. And so we check all the triples, of which there's only one, RTB, and that triple is inactive because it's a V structure where we haven't observed the root or anything descended. So, independent, yes. What happens if we observe T? Well, it's the same path, but now it's an active path. So now we no longer have independence. If instead of observing T, we observe T prime, we still activate this path, and so we don't have independence. Okay. Questions on that? Okay, here's the whole gory example with low pressure and rain and my roof dripping and all that. Okay. L. Okay, is L independent of T prime given that we know the value of T? Well, we look for paths. What paths could connect L and T prime? L to R to T prime. There's only one path. Okay, so we need to know whether or not this path is active. How do we tell? We check all of the triples. And if any of the triples are blocked, then the whole path is blocked. So first we check L to R to T. It's a causal chain, and R is unobserved. So this one is still flowing, right? This one is still active. But then we check R to T prime. that's a causal chain, and there's evidence in the middle, and we know that's an inactive configuration. So the one path here is inactive. That means you can't get from L to T prime, and that means they're conditionally independent. Let's do more. L to B. Can you get from L to B? Well, we've got one potential path. Is L to R to T active? Yes. Is R to T to B active? No. Okay. Remember, V structures are backwards. They're only active if T are one of its descendants. So here, this whole path is inactive because R to T to B is inactive. All right. What if we had L to B and we observe T? Now, L to R to T, that's an active triple, and so is R to T to B, and so we can get from L to B. And if we can get from L to B, then they're not going to be guaranteed conditional independence. Okay, it's the same thing here if T prime is observed. R to T to B is still active, which means this whole path is still active, and so we don't have conditional independence. These are very good to go back over on your own, right? Lots of variables, lots of configurations. It's actually very useful to go over these on your own. Okay, okay, we'll do a couple more. We want to get from L to B, and what's observed? R is observed, and T is observed. So R to T to B, that's active. L to R to T, that's inactive. So this path is also blocked, which means we have conditional independence. Okay. What happens if there's multiple paths? Well, you just check them all. So here's a little fragment. This is that rain causes traffic and also my roof to drip, and I'm sad if either there's traffic or the roof is dripping. Okay. So here we would ask questions like, is T independent of D? Meaning, are there any active paths from T to D? Well, it's the negation of that. So we look for all our paths. Okay, is the high path active? Yes. Is the low path active? No. Okay. If there are any active paths, that breaks the independence. Okay. So what happens if we observe R? Well, now the high path has been broken, and the low path was broken to begin with, and so now there aren't any paths. If you can't find any paths, then they're independent, because there's no way for them to influence each other. Okay. But if we now observe S as well, now the low path becomes active, and they stop being independent. Okay. Questions? Yep. For the last one? Let's just do the last one from scratch. Okay, so we have this graph, and we know we've observed S and R. And we want to know whether T and D in this situation are guaranteed to be independent. They're guaranteed to be independent if all the paths are blocked. So we have to check all the paths. We check the top path, and it is blocked because it's a common cause where the cause is observed. But then we check the bottom path, and the bottom path is a V structure where the root is observed, and that means this one, the one on the bottom is not blocked. And if there's any non-blocked path, then there may be correlation, and so we can't say they're independent. Okay. I'm going to quickly say what the implications of these things are. So what you can do is you can take a Bayes net structure, you take the graph, and you can run the search problem that we just did by hand. If you wanted to, you could run it by machine, and you could get a list of all of the true independence assumptions. Okay? That list of independence assumptions tells you the set of probability distributions this Bayes net can represent. Okay, so if I have, just as a toy example, this Bayes net, x and y, and there's no arrow between them, this can only represent distributions where x and y are independent. But if instead I look at a network of this form, this can now represent all distributions over x and y because no conditional independence properties are guaranteed from the structure. Okay, so essentially every network has a signature of a set of conditional probabilities which are guaranteed to hold regardless of what numbers you put in. Okay, which means you might want to compute all the independences. We're not going to do every single one by hand because we don't have more than a couple minutes, but let's take the top one here. In this top network, what is true? Right? We can consider every possible independence. X independent of Z. Is that true? Nope. That one is not guaranteed to be true. X independent of Z given Y. Is that true? Yes. X independent of Y, X independent of Y given Z. Okay, well, this one's a little bit different because it's just two adjacent nodes, but that one's not guaranteed to be true. So we could go along doing this and compute all of the true independences, and each one of these would have some set. Okay, this one down here, if you look at this one and you stare really hard, you'll see that no independences are guaranteed, right? So this one at the bottom makes no assumptions, and that actually matches the fact that it has a full chain rule expansion, right? Every arrow that could be there is there, subject to acyclicity. Okay, and what this means is a kind of really important point about topology, which is what arrows are in the graph, and the distributions it represents. Which distribution your graph represents depends on which probabilities you fill in under the hood of each node. But if you have this graph that has no arrows, it has all of these conditional independence assumptions, right? Only a very small number of distributions have all those independence assumptions. They're actually really boring distributions. So they might be this kind of small green area. Then when you move up to these graphs all have, even though the arrows are different, they all have the same set of independence assumptions, which is just that X and Z are independent given Y, right? Here you had a ton of independence, so you had a very narrow set of distributions. Here you have one independence, which means it's not all distributions, but maybe it's this red region. There's a lot of things, but not everything. And then when you look down here at these graphs that are fully connected, as you call, because you can't add any more arcs without breaking cyclicity, these ones have no conditional independence assumptions that come from their topology. And that means that by appropriate choice of probabilities of X and Y and so on, these guys down here can represent any distribution. These up here can only represent a tiny fraction of boring distributions. Usually the sweet spot is over here, where the network isn't too complicated, but you still have a constrained set of distributions that lets you make things efficient in a couple of senses. Okay, so we're out of time for today, but basically the summary about representation is Bayes nets compactly encode giant joint distributions. There are some independencies that are guaranteed from the structure of the graph. D-separation's an algorithm to compute them, and the joint distribution might have other independence that you can't tell without looking at the numbers. You'll see some of those later. Okay, next time we'll pick up with how to do inference efficiently.